Before we look at some examples in financial maths, let's remind ourselves of three important mathematical ideas. Firstly, that if a quantity m increases by p%, this means that m is being multiplied by a factor of 1 plus p hundredths. So I really want to convey that it's very nice to work with factors. Also, don't forget to convert the p% into p divided by 100. Secondly, if e to the power of something is 79, that something needs to be ln of 79. An equation like this one, but of a more general look, will be something like 7 to the power of 3x is some old number, for example 343. Such equations are solved by taking logarithms. This is very important to remember. Right, our first example is about Anna, who deposits $3,000 into a bank offering a nominal interest rate of 3% compounded annually. After how many years does she have $12,000? So let's first write down the key. Each year Anna's money increases by a factor of 1 plus 3 hundredths, or 1.03 if you like, but I'm going to keep it like this. That's the key. Work with factors. Then let's say answer is t years. You introduce a letter for unknown quantities, because then you can get an equation. Namely, 12,000 should be the starting amount, 3,000 times this factor by which money increases each year to the power of t. The number of years the money must sit in the bank to go from 3,000 to 12,000. So this is the same thing as 1 plus 300 to the power of t is 4. Now you apply logarithms. So let's take ln of the left hand side is ln of the right hand side. Now by a logarithm law the t can jump down, so you get t times ln of 1 plus 300 is ln 4. ln of 1.03 is just a number, so t comes out as ln 4 divided by ln of 1 plus 300. So that's the number of years it takes for Anna's money to go from 3,000 to 12,000. Now Bo also deposits 3,000 into a bank. This bank also offers a nominal interest rate of 3%. However, his money is compounded monthly. After how many years does he have $12,000? So let's write down the key. Each month Bo's money increases by a factor, so it's again very nice to work with factors, of 1 plus the number of percent by which his money increases each month, and that will be 3 over 12%. So that's the key. Say answer is t years, i.e. 12 t months. So throughout your solution you're really working in terms of months, since that's what is happening with his money from a mathematical perspective. So the equation is that 12,000 should be the starting amount 3,000 times this factor by which money grows each month to the power of the number of months the money must sit in the bank. So you get 1 plus 3/12 over 100, all to the power of 12t should be 4. Now we apply ln of both sides. 12t jumps down. You get t alone as ln 4 divided by 12 times ln of 1 plus 3/12 over 100. So that's the number of years it takes for both money to go from 3,000 to 12,000. Christina deposits $3,000 into a bank offering a nominal interest rate of 3%. But in this bank, interest is compounded continuously. The question is, after how many years does she have $12,000? Now with continuous compounding, things work a little bit differently. The key is the following, that if you have your money in a bank with nominal interest rate R and continuous compounding, each year money increases by a factor of e to the power of interest rate. In this case, 0.03. So not e to the power of 3, of course. That would be a ridiculously good bank. And also, 3% really is 0.03. So the factor by which money grows each year in a bank offering 0.03 nominal interest rate and with interest being compounded continuously is e to the power of 0.03. So with that key in mind, we get an equation if we say that the answer is t years. So as always, introduce a letter for an unknown quantity. Then we get the equation that 12,000 should be 3,000, the starting amount, times this factor, e to the power of 0.03, by which money grows each year to the power of t, the number of years the money sits in the bank until you get 12,000. But this is just 3,000 times e to the power of 0.03t, of course. So we get e to the power of 0.03t is 4. And now you can take ln, sure, or you can just use 2. So by the definition of ln, the 0.03t here must be ln 4. And so t must be ln 4 over 0.03. So that's the number of years it takes for Christina's money to go from 3,000 to 12,000. Here is a calculation about annuities. After each of the upcoming 10 years, Maria will deposit $255 into a bank account with a nominal interest rate of 5% compounded annually. How much will she have after the 10th deposit? Let's first write down a key insight, namely that each year money increases by a factor of 1.05 because interest rate in this bank is 5%, 0.05, and interest is compounded annually. Alright, now we draw a timeline of what is going on. The first deposit is made here at the end of the first year. And in total she makes 10 deposits. Each deposit is of $255. The first one is done after the first year. Now we want to find how much money does she have after the 10th year. let's just say here, so we make 10 our focal time, our time of focus. So really what we want to do is to find the total future value of these 10 deposits. That's to say their value at this point in time. Trivially, the $255 deposited at the end of the 10th year has future value $255. These $255 which were deposited at the end of the 9th year had been sitting in the bank for 1 year. So they must be multiplied by 1.05. The future value of the $255 deposited at time 1, they have been sitting in the bank for 9 years, so to calculate their future value, you need to, go 9 steps forward. And so their future value will be 255 times 1.095 to the power of 9. This is a geometric series, so we apply the formula for a finite geometric series. Is the starting term times a fraction. Down here you have k minus 1, up here you have k to the power of something minus 1, and to go from the first term to the last term, you multiply by k 9 times, so this is going to be 9 plus 1, that's to say 10. Also, here in the denominator you have 0.05, so you're dividing by 0.05 is the same thing as multiplying by 20, so the answer is going to be 5,100 times all of 1.05 to the power of 10 minus 1. And that is in dollars, of course, the number of dollars Maria has in her bank account after her 10th deposit at the end of the 10th year.